The funny thing is that we were calling it the inventory planner, but in this case, actually, it's quite pertinent because we observed that this ensemble of machine learning and mathematical components sometimes was finding solutions which were sometimes similar to what the real planner with available tools was doing, but sometimes it was quite different. Sometimes it was reducing the frequency, sometimes was increasing the frequency, sometimes was timing the orders in a specific way, but it was like a non-trivial strategy, non-trivial order placing policy that this AI solution, an ensemble of these components, was actually proposing.
Welcome to Inside the Algorithm, the show that goes beneath the surface of artificial intelligence into the scientific research, technical breakthroughs, and academic thinking shaping where this technology is actually heading. I'm Jeremy Bradley, Chief AI Officer at Cambridge Spark, a leader in transformational data and AI upskilling, career development, and progression. Each episode, I sit down with the researchers, data scientists, and technical experts working at the true frontier of this field to explore not just what's happening in AI, but also the real science and thinking driving it forward. Whether you're building sophisticated AI systems, leading teams through AI transformation, or driven to understand what's really happening beneath the headlines, this is the show for you. In today's episode, we're going inside the data science operation of one of the world's largest consumer healthcare companies and into two of the most technically ambitious AI projects it has produced. My guest is Dr Gueorgui Mihaylov, Principal Data Scientist and AI Director at Haleon, also Visiting Research Fellow at King's College London, and a mathematician by training whose PhD in pure mathematics from the University of Milan now underpins some of the most sophisticated AI systems running in industrial manufacturing today. Gueorgui led the development of Haleon's AI Inventory Planner, a system that defines optimal corridors for inventory management and is now scaling into an enterprise-wide integrated business planning initiative. He has also been at the center of the Golden Batch project, an attempt to use AI for real-time control in pharmaceutical manufacturing, something that, as you'll hear, remains genuinely novel territory. This is a conversation about where the hard mathematics actually lives inside a global consumer health business, what it takes to move AI from a planning tool to a live control system, and what the end game looks like when you're trying to build supply chain excellence at scale. I do hope you enjoy it. Gueorgui, welcome to the podcast. Thank you very much for joining.
Thank you for the invitation.
So Haleon, for those I'm sure who are familiar, is a huge FTSE 100 business with very familiar brands like Sensodyne, Panadol, Centrum, brands that billions of people buy, interact with, certainly have seen in shops. Can you give us a sense of what data science challenges actually look like inside a business like Haleon?
Yes, the role of data science is quite relevant across all business domains. In fact, we have a relatively big data science team, and we are supporting through various enterprise initiatives all business domains, like, for example, commercial, also marketing, R&D. We have a series of generative AI initiatives and a lot of important initiatives in my space, which is quality supply chain and finance. And yeah, there is a lot of demand and a lot of interesting and non-trivial mathematics trying to solve interesting and non-trivial problems, such as optimizing commercial investment, optimizing forecasting, and optimizing marketing investment by trying to anticipate consumer behaviors. And in the space of supply chain, obviously, large-scale optimization problems in logistics, manufacturing, planning, delivery, and so on and so forth. And we are supporting across all these various domains.
Yeah, that's fantastic. I think we'll get onto some of the supply chain challenges shortly, because I know that's an area you've worked very heavily in with Haleon. So let's talk about the inventory planning and in particular one of the tools that you and your team have worked on over the last few years, the the AI inventory planner for Haleon. So before we get into maybe how it works in detail, can you set the scene for us on what it's actually trying to solve in this space? What was breaking and not working well enough, maybe, and how the inventory planner managed to solve this problem?
So inventory management is a centuries-old problem. However, recent technological developments allow us to have much better digital visibility on processes in complex supply chains such as ours. So basically, the purpose of the inventory planner was to leverage better the digital visibility that we have both upstream on supply. So how exactly our purchase orders are processed and then transported and then delivered. And also leverage better digital visibility downstream, having better demand forecasting and demand sensing capabilities, and combining them in one ensemble of tools or machine learning models, which are able to improve best practices, highlight further opportunities for improving inventory management across the network. So yes, inventory management is quite important, because if you're able to guarantee your service levels with smaller and smaller inventory in your network, this basically allows you a competitive advantage and allows release of working capital, which is always very important for companies.
I mean, that's fascinating and beautifully encapsulates what is, I think, a hugely challenging problem. I mean, you've got many, really thorny issues at the heart of inventory optimization and supply chain problem. A number of you've talked about in previous talks I've seen you give along sort of the lines of unpredictability of supply chain. So how can you give us a sense? I think it's probably one of the biggies. So maybe we just dwell a little bit on that, on how painful and how difficult unpredictability can be for any tool that's going to purport to successfully manage an inventory in a complex supply chain.
So that's exactly the purpose of inventory: buffering around uncertainty, and buffering against uncertainty in demand, and buffering against uncertainty in supply. Uncertainty in supply might be variability of lead times, or alternative delivery channels, or sometimes even serious events like the difficulties that we had a few years ago with the Suez Channel. And this is the reason why, in order to maintain service levels, you need to keep a certain amount of inventory in the network. So that this is the purpose of it, and the fact that advanced modeling is able to reduce it is actually very positive, because it demonstrates direct business benefits, the direct implication in terms of increasing or maintaining service levels while releasing working capital. But yeah, this is not doing that, or doing that not at the competitive level, translates in holding big inventory, being less competitive, holding working capital in our warehouses instead of investing it, and so on and so forth. So yeah, not being able to cope with those stochastic phenomena is quite impactful for all businesses.
Okay, so let's get into it then. So, what can you walk us through the technical core of that model and capturing that noise that you specifically talk to? Because I think that's going to really bring this to life. And what model did you use? How did you capture the noise? What did it? What were the inputs and outputs? And yeah, it'd be really nice to hear a little bit about the detail.
So the inventory planner is an ensemble of several models. We can think of them as algorithmic components, if we wish. So first of all, we have the demand forecasting module. The demand forecasting module, when we started working on this project, was quite advanced, quite state of the art in terms of availability of algorithms. Actually, we used global forecasting algorithms able to cross-learn between different time series in order to in order to improve the performance. But the most relevant part of that forecasting was not producing point forecasts, but producing distributional forecasts. Distributional forecasts built by different techniques, for example, out of sample bootstrapping, to understand what is that distribution of our errors. Because as I mentioned, that was the critical point, being able to understand the distribution of errors and being able to buffer against the likelihood of being wrong, not against the likelihood of being right on a quite variable demand scenario, right? So that was the first component. Second component, as I mentioned, our task was to leverage the digital visibility that we already have in the network. So we created a delivery forecasting model, which was based on survival analysis, and we had like different versions of it, like very simple, like a fit variable distribution from a set of delivery times, or a fit variable distribution where the regression model on the two parameters of the variable distribution can be even a deep neural network that captures all sorts of things like the season or certain specific atmospheric problems on our delivery routes and things like that. So different levels of complexity. So demand forecasting model, supply forecasting model, and that we had and we worked a lot on that, quite interesting scenario simulation engine for our supply reality, right? We had a lot of historical data, which was part of the input of how basically our goods travel around the world. What are some specific milestones that are hit at certain point of the process? We don't have real-time visibility, or we have partial real-time visibility on what happens with our purchase orders, but we have good visibility in the systems on when purchase orders reach specific milestones. So firstly, we use those milestones as intermediate steps or intermediate information in terms of upstream visibility used by the delivery forecasting model. And in fact, the delivery forecasting model was refining its predictions when the purchase order was going to be available in the destination, basically the destination location, and was also gradually narrowing down the confidence range around that. And then in the scenario simulation engine, we are able to execute that hypothetical trip multiple times, compatible with all sorts of very complicated operational constraints. For example, we are able to place an ordinary order, what we call the ordinary order, within certain conditions, right? Of minimal order quantity, incremental order quantities, ordering frequency, make frequency. But sometimes we are also allowed to place what is called expedited order. But there are very serious rules around placing expedited order. The goods that you're ordering must be already in the production schedule. Otherwise, you cannot produce them. Right. So our simulation engine, we created quite a sophisticated simulation engine that was able to simulate delivery and simulate that distribution and supply process in stochastic scenarios, in scenarios affected by stochasticity, but also compatible with that crazy amount of real world constraints. And as a result of that, we created a constraint optimization problem, which was basically give us a business assignment. And the business assignment was, please, your policy, inventory management and ordering policy should be able to guarantee with a very, very high likelihood X service level, because this is basically the commercial constraint. We need not only commercial but also regulation constraint. We need to be able to guarantee certain service levels of our consumer health goods in all markets. So this is the business constraint. And then compatibly with that, we were selecting, basically simplifying down to two parameters: the probabilistic trigger for a normal order and the probabilistic trigger for an expedited order when there was a high likelihood of having a stock out. And based on that, going through multiple simulations, we were able to draw the ISO service level curves, and actually moving along those ISO service level curves, we were able to recommend the optimal policy, which was the optimal ordering policy for normal orders, expedited orders, expected to guarantee a requested service level with minimum inventory.
Wow, that's a heck of a journey. So you're starting with the raw data. You're seeding. You're parameterizing these very fairly straightforward and very commonly used distributions. The Weibull distribution you mentioned, that's often used in supply chain modeling, with the data that you have surrounding your supply chain, and you're using potentially AI models, machine learning models, neural network models to generate those parameters. Was I right with that?
Yeah. To recommend optimal configurations for those parameters. And we actually executed multiple shadowing exercises in which this inventory planner was shadowing the true process, and was actually able to demonstrate the ability of reducing the total inventory position by double digit, 12, 13, 16, 15%, while guaranteeing same or even better service levels. And the funny thing is that we were calling it the inventory planner, but in this case, actually, it's quite pertinent, because we observed that this ensemble of machine learning and mathematical components sometimes was finding solutions which were sometimes similar to what the real planner with the available tools was doing, but sometimes it was quite different. Sometimes it was reducing the frequency, sometimes was increasing the frequency, sometimes was timing the orders in a specific way. But it was like a non-trivial strategy, non-trivial order placing policy that this AI solution, the ensemble of these components, was actually proposing.
I guess finally on that, I'd love to get on to one of the other projects you've been working on, but what does it mean then to scale that kind of planning tool in a global multinational business like Haleon? How did you both get the buy-in, but also then get the operational touch points into the business so that it could advise at every point of the supply chain process potentially for Haleon?
The full, very ambitious and fully automated version of the tool has not yet been fully adopted by the business, despite at certain point we even got President's we were finalists for the President's Medal of the Operational Research Society. However, the learnings or parts of our algorithms, such as, for example, the inventory corridors, the statistical probabilistic calculations of inventory corridors and execution, the simulation engine, the way in which we calculate planning parameters. So all that knowledge is now being implemented in a global enterprise program, which is our program on how we actually do integrated planning across the network. So all integrated business planning solutions and modern platforms, they actually rely on quite serious, quite powerful algorithmic components such as optimizers, simulation engines, a cascade of demand forecasting, algorithms. So a lot of learnings from that project were actually directly implemented in demand forecasting bit, in the scenario simulation bit, in how we compute how we compute the variability of inventory and are prepared for different scenarios, and how that process, the stochastically modeled process, can then feed back in the actual planning process, not just in terms of parameters, but also in, for example, heuristics fine tuning when you actually execute those planning algorithms.
I wanted to move on to another project I know you've worked on with your team in the last few years, and this is equally amazing project involving the sort of manufacturing of your product. So I wanted to talk a little bit about the Golden Batch project. Can you give us a short sort of a pitch on what the Golden Batch project is and why it matters in pharmaceutical and consumer health manufacturing specifically?
The golden batch approach in manufacturing and in pharmaceutical manufacturing is typically a way of formulating what is the optimal manufacturing pattern for a lot or a batch of a product. And can be a combination of, for example, process specifications, regulation targets. The parameters of the batch should be within these limits, and also there is huge space for data-driven study. Sometimes, when the manufacturing processes are long, actually your control variables, your levers, your parameters that you can use to influence the process in real time or whatever time horizon you'd like, actually give you indirect information of what is going to be the final configuration or the final characteristics of the product. And this is quite the case with, for example, glycerol-based toothpaste. Glycerol-based toothpaste, which we manufacture, is an extremely complex non-Newtonian fluid that presents all sorts of challenges in the mixing stage. And the manufacturing process of glycerol-based toothpaste is very complicated. There are many different phases, like around 30 different phases in which different things are happening, like ingredients are added, mixing happens at different speeds and temperatures and pressures, and then you have to cool down the product and so on and so forth. And the control variables that we have are the mixing parameters, actually the sensor readings that we get directly from the mixer. So we worked and found a way to actually influence and control that process through the mixing parameters, to the sensor readings that we're getting directly from the mixers. And quite relevantly, the data-driven component of that golden batch construction, in our case, was quite heavy. Because of the complexity of the fluid, it was very difficult from a purely engineering perspective to design entirely physical control system, which is based on fundamental principles. So we had to very heavily rely on the data-driven part of that, analyzing thousands of batches, finding that optimal golden execution, which realizes the best quality parameters within the shortest execution time.
That's amazing, and the challenge here is phenomenal. And so you've got 30 stages of potentially mixing, cooling, pressurization. How on earth did you manage to establish what the edges of your corridor of appropriate interaction was? The upper and lower limits of your levers, if you like, that you were able to. How did you manage to establish what that was at each stage and unpack it so that you could do that?
Yeah, that was exactly the difficulty. Designing golden corridor envelopes, for example, if you have multiple realizations of a process, is a relatively standard practice in engineering control charts. For example, you can build a statistical replica and understand when the process is drifting out of control and so on and so forth. But this is quite typical for stationary processes. In our case, we had a highly non-stationary process with multiples, and they were in different duration, and it was difficult to recognize the exact time transitions directly from the data. So it posed all sorts of challenges, and we had to work really hard. For example, on the recognition of the phase change directly from sensor readings, which typically are very noisy. But yeah, eventually we got to this smoothened corridor, which was taking into account optimal transitions at the optimal times. And eventually we actually got to scientifically non-trivial results we demonstrated that we're able to keep the viscosity of that fluid under control, standardize the viscosity of that fluid through that highly non-trivial and non-stationary golden corridor, which was Yeah, entirely derived from data and from past and from simulated batches, from past and from simulated batches.
Can you give us a little bit of insight then as to what the architecture for that actually looks like? What the sort of key engineering components were to bring that into reality?
Yes, so this is a question which is interesting not just from a scientific and from engineering perspective, but also in a way from a business perspective, right? Because we started and we completely internally developed this project. So we have to, first of all, demonstrate that it works, having a working prototype, demonstrating that whatever process we develop, they're executable in real time or in near real time. And at that stage of the project, you rarely can say, just buy me a platform to do that, right? So we have to kind of use the tools and the environments and the components of architecture that we have that we already have, and then probably at the next stage of the project where the prototype proves that it works, the algorithms prove that they're efficient, and actually there is some level of demonstrated business benefit. At that point, you can think of more advanced solutions. And we used our available data science toolkit. So we had a execution environment where we actually trained and executed the models. We were able to interface that environment with what is called a data historian equipment, an asset, platform, which we have in different sites around the world, that collects and stores and is able to actually interface with different systems, data streams that come from all possible engineering assets. So this is kind of uh, probably slight alternative to having IoT devices installed on each single device, right? But our engineering assets produced a lot of data streams from all their sensors, and all these sensor readings were directed and managed through a piece of equipment which is popularly known as data historian. So that was the first bit: how we get the data in near real time through the data historian into the execution environment, and then provide the necessary visualization. And the visualization was done through a popular dashboarding tool that you can easily imagine. And yes, so this architecture worked. It was possible. It was quite sufficient from the viewpoint of proving the concept, but it's not a stable solution. It's not something that you can stably rely on. So once the business benefits can be demonstrated, that probably thinking of, like, deploying some of the compute power on, some sort of edge technology instead of centralizing everything in one environment, having much better visualization tools that are more suited for the real-time visualization and refresh, rather than having heavy dashboarding capabilities to do that. Yeah, so there are a lot of learning. One of the difficult points was actually, and it took some time, getting an architecture design approved by security, because obviously there are a lot of firewalls and then security measures put in place on the manufacturing side, so that external environment cannot be interfaced easily with process critical systems. So we had to do a lot of work to kind of, even with our prototype architecture, we had to face some of these serious technical aspects.
And what I loved about the visualization I saw on this was that you called it a sort of manufacturing control corridor for the process that, and then you were able to visualize it. Did I gather, using some sort of principal components analysis, visualize it actually as a corridor? It really does look like a corridor of sort of within this roughly cylindrical sort of hypertube you have to stay.
Yes, it was. In fact, the visualization was based on non-principal components analysis, then obviously evolving over time. But the visualization is kind of simple and nice, whereas the fact that we had to translate a highly non-stationary process to that seemingly stationary and nearly cylindrical hypertube was an interesting part of the mathematical challenge. Basically, making a Shewhart control chart, which is meant to be applicable for stochastic but stationary processes, to make an adaptation, some sort of geometrical adaptation of it, to have an envelope defined by n best realizations of the physical process. But yeah, uh, principal component analysis of the hypertube.
Yes. And when the other nice example I saw here was when the sort of real-time monitoring of the process goes outside of that sort of control window, that control corridor, if you like. And again, beautifully visualized, it sort of turns red and I don't know, starts to shudder or something like that. But more to the point, it gives it then, is it able to then nudge this is what you need to do to bring it within control bounds? Is that the premise, or how much can it go outside of that corridor before you have to go, no, sorry, this isn't going to work?
So at different stages of adoption of something like this. So the first stage of adoption is some sort of if you think in terms of testing at the end of the process, testing at the end of the process is right now mandatory. But if you can prove that processes that have been executed within the corridor without no deviations from the corridor, there is high guarantee for the fact that they are actually within limits, then you can save a lot on potentially releasing some or speeding up some of the testing processes, quality testing processes, even without having a feedback loop for control. And then the next stage would be, okay, what is the best action to recover the batch within the control limit where a deviation is detected. So there are several levels and steps of integration where a tool like that can already start delivering benefits while moving towards the full closed loop, fully automated control system that probably is the end state of something like this. But yeah, I like the cylindrical hypertube because it actually reflects the fact that there is the correlation structure between the 13 or 14 parameters, control parameters that we have, actually highly reflected in the control chart. It's not just about static boxes. Temperature should be between here and here, and pressure should be between here and here, right? It's the correlation structure, which is somehow captured by the Shewhart control chart in engineering, but made dynamical. So yeah, it's an interesting thing.
Oh, very much so. So we've got these two amazing case studies then. You've got the real-time manufacturing control system on the one hand, you've got the inventory control system in the other, both with these lovely idea of a sort of optimal corridor of execution to maintain a healthy system. Is there something sort of unifies them in your mind that sort of brings these projects into a sort of common sort of engineering data science framework?
Yes, in my mind, the common framework that will contextualize both these pieces of work is something that we mentioned earlier during the conversation, which is finding a way to model and to execute an optimal orchestration of a global complex supply chain, which is able to achieve performance, achieve optimal behavior with respect to collective KPIs, to collective characteristics such as overall productivity, overall profitability, overall sustainability. So different projects and different initiatives and different tools that we can build in this context eventually, it would be great if they can communicate and then can achieve this optimal orchestration of a very, very complex industrial system such as a global supply chain.
So finally then, is there a sort of manufacturing or supply chain or industrial sort of AI problem that you think people haven't really sort of got to grips with yet, and that you think is still out there waiting to be tackled using some of these fantastic mathematical techniques?
I am quite interested and passionate in certain topics. For example, the ability of deep neural architectures to capture and mimic the behavior of complex real-world systems. Interestingly enough, a lot of the mathematical tooling that has been developed over the years for describing and capturing the dynamics of complex systems like spin glasses and things like that are now quite relevant in the description and in the deep theoretical understanding of neural networks. Methods borrowed from statistical mechanics, even the geometric deep learning. I'm very passionate about geometric deep learning, being a differential geometer myself. So the interaction and actually understanding one side in order to be able to mimic and simulate, but simulate at a very profound mathematical level, that the behavior of a real world system through a digital replica. That's something that it's quite interesting and quite relevant as a topic. And also really understanding and observing the progress of the reasoning within these new agentic capabilities. So, what is the point up to which reasoning can reach in order to give you benefits, and what is the point beyond which actually the large language model can be an orchestrator of many even more classical tools, such as like solvers or forecasting engines or more traditional simulation engines. So these are and then balancing the benefits between quality of the solution and automation of the solution, right? Because understanding deeply the technical aspects of that, I think very soon it will have like the tremendous importance in terms of articulating business strategies in this space. So yeah, these are two topics that I think are quite interesting and quite relevant in this space.
So, if there were a listener, a practitioner, or researcher who's maybe starting out in this field and thinking, "Oh, this is where I'd really like to commit my time and efforts in the next few years of my career," what sort of advice might you give them in terms of sort of pushing forward and making progress in this area?
Yeah, one piece of advice can be, this is a very promising area. I believe, as I said, the importance and the relevance in terms of direct impact on economy, on efficiency of real world system can be quite foreseeable in the close future. And then personally, I quite believe in knowledge transfer between academia and industry. So I don't have in mind a specific researcher or a person or a persona, right? But I think collaborating with industries, academics collaborating with industries, and also industry being open-minded and curious towards these more advanced methods can be extremely beneficial.
We're certainly aligned on that, Gueorgui. I think both organizations, institutions would benefit enormously from more an open collaboration with each other. So that would be fantastic outcome. I'm sure you would encourage people to reach out if they would like to come and collaborate with you.
Of course.
Indeed. Gueorgui, thank you ever so much for your time today. It's been a real pleasure. Really enjoyed it. Thank you.
Thank you very much, Jeremy. It's been a pleasure, and best of luck with this fantastic podcast.
Thank you for listening to this episode of Inside the Algorithm. If today's conversation gave you something to think about, make sure you subscribe so you never miss a breakthrough, and share it with someone who'd appreciate the thinking. If you're a data and AI leader looking to build deep technical capability across your organization, Cambridge Spark is here to help. You can reach us on LinkedIn or at cambridgespark.com. And if you want to explore AI from the leadership and strategy perspective, check out our flagship show, Data and AI Mastery, with Dr. Raul Gabriel Irma. Until next time, stay curious, stay rigorous, and stay ahead of the algorithm.